Okay, I think it's a couple minutes early, but let's get started. Is the camera on? Okay. All right, so just a few announcements. One is there's a lab due this week. I presume all of you are working towards getting it done on time. It's the end of the semester, so presumably there are multiple courses with deadlines and so on. So manage your time well. Beyond this lab, there is going to be one more homework. Actually, there were two, but I decided to reduce the workload and just cut down one homework. There's only one homework remaining. It's going to be a cloud computing homework based on material I will cover today. Okay, and that will be due the week after the lab, so you don't have to worry about doing two things at once. And beyond that, the only thing that is remaining is the final exam. Okay, as I have announced a few times, the exam is going to be an open book, open notes exam. It's a take-home exam. Okay, I will give it out on Friday, May 5th in the morning. You will have 24 hours to finish it, and you will turn it in via Moodle. Okay, so the next day, which is actually a Saturday. Okay, and then we'll be done with the course. Okay, and the last announcement was last time we were talking about data centers, and that's continuing on today into the cloud discussion. So I had mentioned that I can potentially arrange a field trip to a UMass owned data center, which is in Holyoke, about 10 miles from here. Okay, I'll make an announcement through email with a sign up sheet. Okay, they can accommodate, each group can have at most 20 students as far as the tours are concerned. And they said that they can accommodate at most 2. Typically they only do one group per class, but in the class is larger, I don't know how many students are going to sign up to go. And I'm going to have it the week after final exam. Okay, that's the final exam week itself, but at least this course will be done. So sometime on week of May 8th or some such thing, I will have an optional tour. It's completely optional. You don't have to go if you don't want to. But if you want to come see a real data center, you have the opportunity to do so. Okay. So I will announce that. You can sign up, and then we'll see how many students want to go. All right. So with that, let's continue our discussion from last time. I was talking about data centers and cloud computing. We covered data centers, and we were actually just starting the discussion on cloud computing. Okay, so a cloud platform is essentially a data center where the resources, the computing and storage resources, can be leased or rented by customers. So rather than having to buy your own servers, you can rent servers, and you can rent them by the hour. In some cloud platform, you can rent them by the minute. So the billing is based on the time you use a server, or for storage, it's obviously the amount of storage and the time you use that storage resource. Okay, so it basically, it's a remotely available data center. It has a pay-as-you-go model depending on how many servers you use and how much storage you use. At the end of each month, you get a bill for that much usage, and that's what you pay. Okay, so you don't have to buy your own infrastructure. It's highly scalable in that if you need more resources for your application, you can just ask for more servers, and then you can be given those servers. And it is a shared data center in that there will be multiple cloud customers. Each customer will have some number of source servers and storage within that data center. So there will be other customers using other servers. Okay. Now the important thing is the entire data center is virtualized. Okay. So essentially when you get a server, you're getting a virtual server or a virtual machine. Okay. So you'll just log into that virtual machine and start whatever application you want to start and whatnot. Okay. So let me, so when you talk about cloud computing, you can actually rent resources at different levels of the software stack. And depending on what kinds of resources you are actually renting from a cloud provider, you have different kinds of cloud platforms. And these are the three that are very common. One is called infrastructure as a service cloud, or IaaS cloud. There's a platform as a service cloud, or a PaaS cloud, and there's a software as a service cloud, or a SaaS cloud. Okay, so, software as a service offerings you may have actually encountered. If you have something like Google Apps or Google Mail, or even things like Dropbox. So all of those are essentially cloud-based software services. that can provide you storage service, email service, all these kinds of services. And so they come under this umbrella of a software as a service cloud. Okay? Now, personal Gmail is free, but these kinds of services are also available to organizations where you can pay on a per user basis every month. Okay? So, in an infrastructure as a service cloud, you're essentially renting servers and storage. Okay? In a platform as a service cloud, you essentially deploy an application on a platform. You don't have to worry about how many servers you need or how much storage you need. The platform will take care of it for you. Okay? And then you essentially the scalability is handled for you by the provider, and you can, if you get a software as a service cloud, you do not have to worry about getting certain number of servers or even a platform. You just use the software and you are built based on how you are using that software. Okay, so those are basically web hosted software suites. Okay, so I'm going to talk about the first two, which is an infrastructure as a service cloud or IaaS cloud and a PaaS cloud. Okay, so there are many examples of an infrastructure as a service clouds. Amazon runs a very large cloud platform. Microsoft runs the Azure cloud platform. Google runs a Google computing engine platform. Then there are many other providers as well. Okay, these are the three big providers. So I'm going to briefly talk about Amazon because the next homework will actually involve using Amazon's cloud and trying to understand infrastructure cloud services. Okay, if you haven't used it, that homework will make you familiar with it. So essentially this allows you to rent servers and storage to customers. Okay? And what the cloud provider will do is they will have their own data centers. Amazon actually has a global network of data centers, each in a different continent or a country. And when you request a server, you say, I want it in this region. Okay, so you will have a US East region is actually located in Virginia near Washington DC. Kind of US West, you will have data centers in many countries in Europe, your data centers in many countries in Asia and Australia and so on. So you specify which region you want a server and how many servers. Okay, the other thing that you can do then is also decide what type of server you want. There are different kinds of virtual servers you can get. Here are three examples. Okay, this is how they started. Now there are dozens of different kinds. So in the early days you could get a small server, medium server, or a large server. So that's a label that they associated with the server types. And as the name suggests, as the server gets larger, you get more resources on the server. A small server essentially gives you one virtual core, okay, one core machine, about 600 megabytes of RAM, some amount of disk storage, okay, is basically that configuration of the server. And the cost is around, this is still old numbers, it's around a penny an hour. Okay, so 1 cent an hour. That's the cost that you are going to pay. So if you rent it for a whole month, you might pay on the order of a few tens of dollars. Okay, so that's how much you're going to pay to rent a small server. Okay, medium server has maybe 4 to 6 cores here. This particular one has 5. You get more memory, you get more disk and so on. You can get large cores, large servers which will have maybe 16, 32 cores and things like that. And if you actually go and look at Amazon's offering, or for that matter Microsoft or Google's offering, you'll see that there are a dozen different configurations to pick from. There'll be servers that will have SSD disks, there'll be servers that will have GPUs. So depending on what you need for your application, you can say, give me N of small servers, give me 5 small servers, and then the cloud will provision those servers and say these are the IP addresses that you can then use to log in. Okay? So that's basically how an infrastructure cloud works. You have to create an account, okay, set up an account, and then you can request resources, which would be more in this case server resources, and you can also request storage resources. Okay, you can get there are different kinds of storage even within Amazon. Okay, so you can get what is called elastic blocks service, where you can say I need a volume with so many gigabytes. You can create object-based storage, which is called Amazon S3. So and that also costs certain number of pennies per month. Okay, so here the cost of storage is 10 cents per gigabyte per month. Okay, so based on how much disk space you're using, you will get billed every month. Okay, and then depending on how much bandwidth is going in and out of your machines, they also charge you for network bandwidth, which is, as you've seen here, it's about 10 cents per gigabyte of bandwidth. Okay, So that's an example of an infrastructure cloud. So the model is customers create an account and you go and say, I want these kinds of machines, these many machines, so much storage, and because it's virtualized, you can basically the cloud provider will allocate you those machines. They will get mapped transparently to some physical servers in the infrastructure. As you'll see here, there's a green customer, a red and a blue customers, and they requested certain numbers of machines and they've gotten mapped to these racks in your cloud data center. Okay. Any questions on infrastructure cloud, how that works? Okay, so your assigned cloud homework will actually make you go get a machine and do some interesting things with it and get some storage and so on. So you'll get familiar with all of those things. Okay. Now the other kind of cloud is a platform as a service cloud, which is called a PaaS cloud. Okay. There are many examples of this as well. Microsoft Azure started as a PaaS cloud. There's something called Google App Engine, which is also a PaaS cloud. So what happens in a platform as a service cloud is, rather than saying I'm going to get a server, then I'm going to install the OS and install my applications, you basically just take your application code and you deploy it on the PaaS cloud, and then it is up to the cloud provider to figure out how many requests are coming in to that application, how much resources to provide. You don't worry about it. They'd worry about, okay, what kind of server should I put this application on? As the number of requests goes up, they can internally replicate it or do whatever they need to do in order to service your request. So it takes away the complexity of figuring out, if I want to run a new web application, what kind of server should I get? How big should it be? Because if you under provision and you get too many requests, your server will get overloaded. And requests will be turned away saying service is saturated. So you don't need to worry about those things. And so essentially it gives you a highly scalable execution platform. You can write your application in things like Python or JavaScript. There are different kinds of platform offering. You can write it in Java, depending on whatever that platform provides. There will be certain number of languages that are supported. You write your web application using those languages, you just deploy it on the platform and it will run your application for you. Okay. So it is basically, you don't need to virtualize the servers themselves here, because the platform is taking care of it for you. You don't even worry about servers, you just deploy your application and you are built based on usage of that application. Okay, so App Engine actually supports Java and Python based applications. Okay, there are other providers that will support other kinds of applications as well. Okay, so it is a different layer that you are actually renting resources at your end, essentially renting platform resources rather than server and storage resources. Okay? And as I said, the highest level of the stack is software resources. Software as a service cloud, where you are actually going and essentially creating an account on a software stack, and you don't even need to write your own code. The application is written and pre-configured for you. You can just go and start using it. And there are many examples of web hosted applications that you may have yourself used. I gave you an example of Gmail as just one of the many. Okay? So that's called a software as a service cloud offering. Any questions on the layers of the stack? Okay, so the other dimension to think about cloud platforms is whether it's a public cloud or a private cloud. Okay. Cloud providers like Amazon, Microsoft, Google, they run what are called public clouds. In the public cloud, any customer can basically create an account and request cloud resources. Okay. So you just need to then pay them on a monthly basis depending on how much you use. Okay, a private cloud is essentially the same idea, but for a cloud that is serving a particular organization. So its resources can be used by users within that organization. So each organization, so let's say UMass sets up its own cloud. So any faculty or student can then go and request resources on the UMass cloud, just as you could go and request resources on the Amazon cloud. But that cloud is only open to users within that organization. Somebody outside cannot just come and say, can you give me machines on your cloud? Okay, so private clouds are cloud data centers that run cloud like offerings, but restricted to an organization. So they are private to an organization. Okay? So there are many companies that use the same cloud model, because it is advantageous over statically allocating resources or servers to users within an organization. Because you can go request a server, and when you're done with it, you can relinquish that server, and then the free resources can be used by other users. Okay. So the same model is now used within many organizations, and essentially that organization needs to have a private data center, it needs to virtualize them, and it needs to provide an interface. It could be a web console where you can log in and say, give me 3 machines. Yeah, I need them for 10 days. And then you will be given 3 machines for 10 days. And then once you're done, you say, free those machines, and they go back to the idle pool, and other users can come use it, and so on. Okay? So that's a way to share a large cluster of servers or their resources in a data center across users within an organization. Okay. Now you can take a public cloud resources and a private cloud resources and mix them up to serve your own needs, and this is referred to as a hybrid cloud. In a hybrid cloud, initially when you request server resources, you might prefer to put them on your private cloud. Okay. But let's say all the machines on the private cloud are in use. Let's say you have 1,000 machines, but all 1,000 machines are in use by users in that organization. If users within that organization want additional machines, then you can temporarily borrow those machines from a public cloud provider, but give it IP addresses using things like VLAN technology or virtual private network technology, so that just looks like machines within your organization, except that the machines are actually being used on a public cloud. Okay. So essentially what this says is, whenever your private clouds are overloaded, you can overflow into a public cloud and just get machines from there. And when you have more idle resources, you can just move the application back into your private cloud. This basically allows you to make better use of resources within your cloud and not have to depend only on a public cloud. You only do it whenever your private cloud is overloaded. So these kinds of hybrid models of our cloud platforms are also used by organizations, where they overflow into public clouds whenever private resources are overloaded and things like that. Okay, so now the specific example I gave you is called cloud bursting, where if you are overloaded, you basically overflow into a public cloud. So this overflowing into a public cloud is referred to in industry terms as cloud bursting. Okay, just some term that you might encounter, that's what it actually means. Okay. Now as far as what kind of applications you run on the cloud goes, there are a variety of different things you can do. You can run traditional client server applications, multi-tier applications, everything we have seen repeatedly over the course of this class. So web servers, databases, and all of those can be. Cloud servers are also heavily used for batch processing. If you have large data sets, if you want to take a large data set, process it, okay, that's a very good use case for the cloud, because you don't need to do very long-term processing. Okay, once you're done with processing the data set, you can give up your servers. Okay, so you just have some large amount of data, you temporarily need resources to do the processing. Okay, so batch processing of applications is a popular use case for cloud resources, where you temporarily need those resources. And we will talk about, when we now move on to middleware as our next topic, we will talk about data intensive computing, specifically using models like MapReduce and Spark, which you may have heard of, Hadoop and things like that. So these middleware systems are designed specifically for processing very large data sets. Okay? Your data sets may be terabytes or petabytes in size, and these frameworks allow you to efficiently process these very large amounts of data in parallel using commodity clusters. And running them on the cloud is also a very good use case, because many of the times you don't need the machines for very long periods of time. Once you're done processing your data, you can give up those resources. Okay, so essentially client server applications, batch applications, large data intensive computing, they're all good examples of what kind of workloads typical cloud platforms see today. Okay? Any questions on this? Okay, I think that I might have one or two more slides and then we are done. So cloud computing is still very much an active area of research. There's a lot of ongoing work in this area, and there are many different issues that people have looked at. I just listed three. One is security and privacy, scalability, and programming models. Okay. Security and privacy says that how do you guarantee security and isolation of cloud resources to customers. Okay. Typically, when you are renting resources, you don't own the underlying server. You rented it from someone else. They own the machine. Okay. In fact, they have root privileges over that machine. Yet you are putting your application and your data on somebody else's machine. Okay. You want to make sure that your data is secure. Okay, that the cloud provider has put adequate safeguards on those machines, because if there is a problem with the machine and there's a security breach, your data is lost, okay, or your data gets compromised. Okay, so privacy and security of cloud resources is an important problem, because you are putting your data on essentially some third-party machines and third-party storage, which is, so you can assume that there is some level of, there's less trust on someone else's machine, and if you own the machine, you completely control the machines, right? So how do you do secure computation on untrusted resources? It's an active area of research, and it directly applies to the cloud model, because cloud resources are owned by the cloud provider. The data is owned by the application provider. Okay, so that's an important issue, and it may not just be a security issue. Just because there are multiple customers using cloud resources, you might get performance impact. If one application belonging to some other customer starts misbehaving or gets overloaded, it might impact your application, which is hosted on the same machine but on a different virtual machine. Okay. So providing isolation between virtual machines that run on physical servers is another important issue that you have seen in this area. Okay. Scalability just says, how do you as a cloud provider manage a very large infrastructure? Okay. Each of those data centers might have 100,000 servers or more. Okay. And you have to now manage those servers, allocate machines to customers as they request them, and so on. So you want to scale your data. So this is a very large distributed system. So you scale your algorithms and resource management techniques to very large scale systems. Okay, that's an important challenge as well. And the third challenge is a user specific challenge, which is if you want to write a cloud application, what are good programming models? Okay, because typically if you want to write it in a scalable way so that you can use lots of parallel resources, how do you program it? How can these programming models make it easy to deploy your code quickly on a large number of machines with minimal effort? Okay? So it's not just writing the code for your application, also deploying the code, configuring it for the machines to talk to one another. If all of that is made easier for you, you can then write distributed applications and deploy them more easily. Okay, so that's another challenge that many of the researchers are looking at. So this, as I said, that's an active area of research, so there's still a lot of ongoing work, but there are lots of commercial cloud offerings as well. And in the next homework, you will actually go and look at Amazon's cloud. So anyone here used EC2 or Azure? Okay, so some of you have. All right, so now you will use some more of it this time. Okay, any questions on this? Yes?
So Docker as a service will come in the PaaS, or it's like an application?
Can you repeat the question?
Docker as a service?
Okay.
So will that come under the PaaS thing, or it's like an application?
Okay, the question is Docker as a service, is that a platform or is that an infrastructure? So Docker as a service looks more like a platform offering. Okay, it's not a software, because you are basically using, you're deploying, it's a mix between a platform and an infrastructure. In an infrastructure as a service cloud, you are renting bare bones servers. Okay? So you just get a server, and then it's your job to deploy an OS or whatever you want. It's like just as you go buy a new machine, you are getting a server. Okay? That's all you get. In a platform cloud, there's some software is pre-installed for you, and you are just deploying your code to run on the server. Okay? You are not configuring the software on the server. Now Docker is somewhere in between. Okay? Docker allows you to install container virtual machines, not hardware virtual machines, and depending on, so that looks like an infrastructure cloud where you say, I want to deploy 5 container VMs on servers, and the cloud provider will then map them onto that server. But having said that, there are some aspects of it that also look like platform offering. So in some sense, it's more closer to infrastructure, but there are some aspects of a PaaS. Okay? Doesn't cleanly fit in. Other questions here? Okay. So I'm going to switch gears and move on to the next topic, which is distributed middleware. Okay, so today for some part of next class, I'm going to talk about distributed middleware systems, of which there are many. I'll talk about DCOM, which is basically Microsoft's middleware system. Talk about Corebar, which was developed in the Unix world, not very widely used anymore. I'll talk about enterprise Java Beans, which is still widely used to deploy web applications. I'll talk about Genie, and then beyond that, I'm going to talk about other middleware system for big data processing, which is MapReduce and Spark and things like that. Okay, so these will be quick case studies just to give you some flavor of if you wanted to use a middleware system to write your code and deploy it, what kinds of middleware systems are out there, and what kinds of features they provide. Okay, we are not going to go into any one system in a lot of detail. Rather, we are going to look at a whole bunch of them from a conceptual and architectural standpoint. Okay, so let's start with distributed objects. We looked at this when we were talking about RPCs and RMIs in chapter 3. Okay, so you already seen this picture where you have a client, there's a server. Okay, you have objects that are distributed across machines, and then client can make method invocations on a remote object. Okay, that's basically remote method invocation, or RMI. Okay. Now in many cases you will have lots of different objects. The objects might get replicated and you might have to make calls on multiple objects and so on. Okay, so this is a very simple case where there's one remote object and one client, but there could be more complicated examples of how you write distributed applications as well. Okay. So essentially RPCs give you basic features like marshalling, demarshalling of arguments and so on. Okay, and then in the object-oriented world, you essentially get objects that are distributed across multiple machines. You can make method invocations on them. Okay, and so that's just a recap of what we have covered already, okay, and previously. So here's a quick slide that shows you historically various kinds of systems that have been built, middleware systems that use distributed objects, and where we are today. Okay, so RPCs started off this whole area, and they were obviously not object oriented, and that grew into RMI. So there was DCOM, Corebar, Java RMI, which we already covered, and that's evolved into enterprise Java Beans and so on. Okay. And in the old days, they assumed that your distributed application would look something like this, where the circles are nodes and an edge indicates which component of your application or which node communicates with which other node. Okay, so it says, I will distribute my application across these 6 nodes and they will interact in complex ways. Okay, so a lot of the middleware systems were built assuming that's how applications are going to be using them. Okay. But what you see, which is the common case, is essentially this. It's a client server. Okay. Not 20 components that all interact. Essentially, there's a client component that's making a call on the server component. It might so happen that the server component might be a multi-tier application which has 2 or 3 other components, but that's about it. Okay. So essentially that vision has never come to pass because most of the application deployments are much simpler than that. As a result, what you will also see historically, some of these middleware systems were essentially failures because they were designed for this more complex case and ended up being a lot more complex than they needed to, which made them harder to be used. Okay. What succeeded eventually were middleware systems that actually were tailored more for this model, which is a simple client-server model, okay, which is what is actually more common. Okay. With that, let's talk a little bit about each of those components, or each of these systems rather, not components. So I'm going to talk about Corebar, DCOM, Java, Enterprise Java, and so on. Okay. So here is a slide that shows you how object references work within Corebar. Okay, remember that when we did Java RMI, I said you can pass objects by reference. Okay, in RPCs you could only pass parameters by value. In RMI you could pass objects by reference. We never actually said how that even works. Okay, essentially reference is when you pass anything by reference, you are passing a pointer. Okay, but you cannot pass a pointer across machines because pointer is a memory address local to that machine. Okay, so whenever you are passing objects by reference in a distributed system, you have to essentially pass a network pointer. Okay, a network pointer will involve information about which machine that object resides on, okay, and how to contact it in some way. Okay, and this slide is, or this figure rather, is showing you the contents of an object reference in Corebar, which is essentially the equivalent of a network pointer. And you will see there are lots of fields in that object reference, but you will see that there's a host IP address. Okay, there's a port number that tells you how to contact that the server application on what port, and there's the object key, which is essentially your object specific memory reference. Okay, so we have to, in order for us to pass object references, we have to generalize the notion of passing pointers, which are simple memory addresses, to making them look like network pointers. And a network pointer will have at least 3 components, which you see here. Okay, an IP address, which says where does which machine does this object reside on, port number, which is where is that application or server listening on, and the pointer to that object or a reference to that object, which is shown here as an object key. Okay, so this is basically just one example of how these distributed systems pass object references around, and then when you dereference an object reference, okay, you will basically say this is how I can contact that object. Okay, so it's no longer a simple memory address is the way to look at this. Okay, now let me start with some examples of EJBs or enterprise Java beans. So this is still a widely used middleware platform today. Okay, you all programmed in Java, I presume, or are familiar with programming in Java. If you want to take some Java code that you have written and deploy it as a web-based application or a multi-tier application, you will essentially use an enterprise version of Java. Okay, typically the Java you are using is what is called Java Personal Edition. Okay, it's meant for writing simple Java application. It does support RMIs, but not a whole lot more. In an enterprise Java case, it's basically the same Java code, but it gives you more middleware-based services. In particular, you will see that enterprise Java supports JMS, which is Java Messaging Service. There's JDBC, which allows you to connect to databases. There's Java RMI, that's standard even in traditional Java, and there's basically some network services that are provided to you as well. So these services are now provided by EJBs as middleware services that allow you to send messages, connect to databases, do your RMI calls, and to network services and so on. And what is shown there, which are labeled EJBs, are essentially your Java objects. Those are the classes you write that essentially becomes objects when you run your code. Okay? So your code is running exactly the way it runs on a JVM, except that your J2EE JVM will support additional enterprise services, which essentially make it a more powerful middleware system than basic Java. Okay? And let me show you a little bit about how this works. So just as you write any Java application, okay, you essentially have to take, when you write a class for a EJB application, you have to write what is called the interface to that class, which are what are the methods that are exported, the public methods, okay, which can be invoked remotely. Okay, so these are all public methods that are remotely invocable. So that's essentially the interface. Okay. So the remote interface are remotely invocable methods, the home interface are the local ones. Okay. And then there is going to be the implementation of that object, or the class rather, which will contain the code. Okay. So you will have to define the interface and you have to define the implementation. Okay. So it basically separates the interface from the implementation. Okay. And when you write a Java EJB class, okay, you have to choose between 4 types of classes that are actually supported. Okay. In a Java class, you just have a notion of a class. In this case, you have to decide what type of a class it is. Okay, so essentially the classes are called beans in EJBs, which is where the name comes from. Okay. just like there are coffee beans, these are called Java beans. So the traditional one is called the stateless one. Is called stateless session bean. There's something called stateful session bean, the entity bean, and message driven bean. So message driven beans are meant for sending messages back and forth. They give you a messaging interface. Okay, so those two there essentially have this notion of a session, and one can keep state, the other is stateless. Okay, so this allows you to write distributed application where client connects to the server. Okay, you create a user session. Okay, then you can make repeated calls, and then that class or the object rather will keep track of your state. Okay, if you use a stateless version of a session bean. If you use a stateful version of a session bean. If you do not want to keep state, you can pick the simple stateless version. Okay, the main one is an entity bean. Okay, this one can persist state across on disk. So even across application restarts, your object state is actually serialized and stored on disk. Okay. I don't know if anyone of you used Java serialize or deserialize. Okay. So you can actually take an object and write it out to disk and then reconstruct it by deserializing it at a later time. Okay. All of those are automatically done for you. Okay. You basically say this is a persistent object, which means that even if your application is shut down, your middleware will write out that object onto disk, and when you restart it later, you can reconstruct that object. So the object doesn't go away even across restarts of your application, which you typically don't get as a Java class. You have to manually write out state and recreate it if you wanted to do that. Okay? Or this middleware will automatically do that for you. Okay? So those kinds of objects will live across application restarts and so on. So you get more flexibility in how you write your Java code, what kinds of classes you want. They are designed more for client server applications because you can say, should you have state or not, right? And do you want to keep track of sessions or not? Do you want to persist the state on disk or not, and so on. Okay? So more advanced features than traditional Java application. So that's essentially what enterprise Java will give you if you have written enterprise Java application. And when you run enterprise Java code, you have to run it on a special kind of a server which is called a J2EE server. Okay? So EE stands for Enterprise Edition, which allows you to run the code, and then it's designed more for RMI style client server invocations, okay, as opposed to just simple standalone applications. Has anyone written a J2EE application? No. Okay. All right. So that's a very quick overview of Java middleware. Okay, now I'm going to talk about Corebar middleware, which is another middleware system. Okay. This was actually much older or predates J2EE by at least a decade. Okay. It's actually one of the early distributed middleware systems that were built. Okay. And it has some differences from some of the others that we have seen. Okay. So you will see that this is the architecture of Corebar. You will see that there's a layer here called the object request broker, or an ORB. Okay, that is fundamental to this notion of Corebar. Okay, so that's basically your communication plane. Okay, then so a request broker essentially allows different objects to send requests to one another. It's brokering requests. Okay, so if you want object A to communicate with object B, then messages flow through the ORB. Because ORB is essentially facilitating that communication for you. So ORB is the core of the middleware platform. It handles communication between objects and clients, and it will do a bunch of additional things that we will see. Okay? So that's the core of this distributed middleware. So that's your communication plane for your middleware. Okay? Here are where the applications reside. Okay? If you write an application using Corebar, they will basically be sort of sitting in this box, and all of these other boxes are services that the middleware will provide for you. And I'm going to show you a table that will list various common services, and you will see there are domain specific services, general purpose services, and then there will be certain core services that just facilitate communication. Okay? And just to make that more concrete, here are all the different kinds of services Corebar will support out of the box for you. So you don't need to write any code for it. Okay? If you want threading in your code, you just use a concurrency service and it will make your code multi-threaded. Okay? If you want To have persistence, you use persistent service, the same as enterprise Java beans, the entity beans, you can persist your objects on disk and so on. If you want to secure communication, do encryption and so on, you can actually have a security service. Okay? You will see that if you want to write querying to databases, there is essentially a query service. Okay? If you want to implement transactional features, there's a transaction service. Okay? So what the designers of Corebar did is they said what kinds of distributed applications might people want to write. What kinds of functionality would those applications need, and they took each of those functions and made it a service. Okay, so now when you write your code, you don't need to write code to do those functions. They are actually supported by the middleware or the libraries that the middleware provide. You simply use those libraries to implement threading or querying or event notification and a whole bunch of these services. Okay? Now, so it looks like a very powerful middleware system, but it's also an extremely complex middleware system because it has so many built-in features. Okay, the overheads of using the middleware or this middleware are substantially higher than other lighter weight versions of middleware. Okay? So the learning curve to write Corebar applications is much higher than if you wanted to, let's say, write a EJB application, because there's a lot less functionality that's actually put into the middleware itself. Okay? So as a result of this complexity, Corebar as a middleware system never actually took off. Okay? There are relatively few real systems that ended up using Corebar because it was too complicated for many people to use. Okay? The one that is still common that you see to even today, Corebar is at this point very old, but there's one system that still uses it, and that's the GNOME windowing the system in Linux. Okay? If you use Linux, you know that traditionally there used to be KDE and GNOME as their windowing system. Now there are a whole bunch more. GNOME was actually built on this notion of Corebar. It has this notion of a network object. Okay? So it's essentially a distributed object system internally. It uses network object and is Corebar based. Okay? So that's the only one that's actually still used today. And of course it doesn't use a whole lot of these services at all. It basically uses a very stripped down version of Corebar that's customized for the windowing system. Okay. So if you look at the object model, it looks like any other client server model. Okay, so you will see there's a client application on the client machine, server application that implements a server object. Essentially your stub is now here, okay, and then you have the orbs sitting on both the client and the server that they all perform the communication, the RPCs and so on. Okay, so since I said the orb is facilitating communication, essentially your server and client stub in a typical RMI systems have been replaced by the client orb and the server orb. Okay, and it handles all the runtime object-oriented communication. Okay, just as you write RMI code and you have to essentially write some interface definitions, there are compilers that will compile that into code that you link to your application and so on. So all of those services that you see in RPCs and RMI systems are also present here. Okay. Any questions on this? Okay, so I'm going to show you some additional details. Okay, so you will see that Corebar also supports different kinds of RMI calls. Okay, we talked about synchronous RPCs, asynchronous RPCs, deferred synchronous RPCs. All of those are actually built into Corebar. So when you make calls, you can say what kind of calls you want. So you'll have one-way, synchronous, deferred synchronous. They're all built in here. Okay, so this was the first system that implemented them, which is where those ideas actually came out from. Okay, most traditional systems just do synchronous. Okay, here you get a choice of which one you want to use. Okay, so lots of bells and whistles, and the one particular service that I'm going to talk about is essentially the event and notification service, which was listed in this table. Okay, you will see that there's the event service and a notification service. So you can use the event notification service to essentially implement a publish subscribe model, okay, or what is called a pub sub model. Okay. So in a publish subscribe style distributed application, okay, essentially you have two kinds of entities. Publishers create data, okay, and they somehow have to then send that data to consumers. Okay, so the consumers subscribe to data. So there's producers and consumers. Producers are also called publishers, and consumers are going to subscribe to data. So when a consumer might say, I want any data that is created that matches certain attributes, okay? And then whenever any data is created by any publisher, essentially it is then, depending on the match, it will be delivered to the consumer. Okay? Now Corebar provides an inbuilt service for doing this or writing pub sub application, which is called the event channel, or the event service. So what you will see, event channel is essentially an intermediate buffer. Okay? Your suppliers are essentially publishing data and then sending them to the event channel, and the event channel will then say which data needs to be sent to which consumers. Okay? And here you see a push-push model where the data is pushed from the publishers into the event channel. The event channel is actually pushing them to the consumers, depending on which data is matched with which consumer. Okay? Not all data will be sent to all consumers. And you can of course have pull models as well in events or in Corebar. So in this case, the event channel will periodically poll publishers saying, do you have any new data? If so, you basically acquire that data, and the event channel will keep track of all the subscriptions, saying what kinds of data is of interest to what consumers, and whenever any new data is created, it will queue it here, and the consumers also periodically poll the event service. Okay? And you can have any combination. So you have here you have push, here you have pull, but you can say the communication between the event channel and publishers is push, but the communication between the consumers and event channel is pull. In that case, you have a push-pull model, or vice versa. Okay? You can essentially have all of those styles of communication between consumers and suppliers. Okay? So this is one example of how you can write publish-subscribe style applications. Okay? Now there are many examples of where such applications are useful. Okay? In your lab, you essentially wrote multi-tier applications to process sensor data. A publish-subscribe style application is very well suited for these kinds of data. If a sensor produces a data, you can publish it to the event channel, and there may be certain other applications that may have subscribed saying, if there's a motion, send that data to me so I can raise an alert. Okay? But I don't care about light sensors or other kinds of sensors, so I only want to subscribe to motion event. So all sensor events will flow into the event channel, and depending on what kind of consumer code it is, it might only get some subset of them delivered to it, and it can process it. That's one example of an application that is actually well suited to this kind of publish-subscribe style paradigm. And there are many others. Whenever there's any steady creation of data that you want to process, okay, you can use a publish-subscribe model. You can also use other kinds of stream processing application. Okay, so this is one example of how you can write a distributed application. Now Corebar of course supports this, but there are many other publish-subscribe systems as well. Okay, you don't have to use Corebar to do this, but this is a good use case to understand the publish-subscribe model. Any questions on this? Okay, so this is just an example of polling in a publish-subscribe paradigm, where essentially you still have to use the orb to implement the event service, and there's a callback interface. So essentially you will register your request saying, if new data arrives, notify me. I'm not going to poll periodically, but I would like you to notify me if new data arrives, at which point I will poll. So for that you will need to specify a callback interface. You'll register that with the orb, and whenever the event service sees new data that matches, you will basically get an asynchronous notification, and then the consumer can actually go pull the data from the event service. This basically eliminates the overhead of periodic polling, and you only communicate with the event service when there's new matching data for you. Okay? Alright, so yes, just messaging. Okay, so the last middleware system I'm going to talk about is Microsoft's system. Okay, and today this is actually evolved into what is called .NET. Okay, if you have programmed in the Windows world, okay, you will see that .NET is now the standard for writing client-server application. So that's the Microsoft distributed middleware system. Okay, but there's some history that goes back some number of years that led to what is called .NET today. Okay. So I'm going to talk about essentially several different middleware systems that Microsoft has built for the Windows world over the years. Okay, and essentially we'll start with DCOM, but DCOM itself has some predecessor. Okay. So DCOM stands for Distributed Component Object Model. Okay. It's essentially a very similar distributed middleware that provides distributed object. Okay. And DCOM itself has a number of components. Okay. At the very base is what's called COM. COM provides you simple client-server communication. As you will see, there's a COM library, you have objects, and you can essentially do RPC or RMI-like communication. Okay. This was the oldest middleware that was built maybe now 20 or more years ago by Microsoft. Okay. And when they built COM, or the reason they built COM is there was a layer on top of it called OLE, which stands for Object Linking and Embedding. Okay. And that was inspired directly by Microsoft's Office suite application. So if you know, if you have used Word and Excel and so on, you know that you can take an Excel spreadsheet and embed it into a PowerPoint document. Okay, and then make a chart from that document. So Excel will have some data, can convert that into some sort of a graph and embed that into a Microsoft document. Okay, so essentially, and that is essentially using object linking and embedding, or embedding one object into another. Okay, from an object-oriented standpoint, whether you have a PowerPoint presentation or a Word document or a spreadsheet, they look like objects. Okay? The objects might have other objects. So you have a Word document, it might have an image, it might have some text and so on. So what you can do simply is take some part of an object and embed it into another object. Okay? And when you try to then invoke that object, essentially you have let's say PowerPoint communicating with Excel services to say, how do I render this spreadsheet and make it look like a graph? Okay? This allows you to essentially use certain kinds of documents and put them into other documents. And this is how they designed essentially this document linking and embedding. Okay? And which uses RPC communication between, or RMI style communication between Word and PowerPoint and Excel and so on. Okay? So that is why they designed their original RPC system. They wanted Office applications to communicate with one another, allow users to simply drag and drop things from one document to another using this kind of features. Okay. Now, over the years, obviously, you can now use that to write other more general purpose application, not just Office application. Okay. Now, layered on top of OLE is what is called ActiveX. ActiveX was a layer that was designed when the web became popular. It became common to essentially write web applications that had built-in controls and so on. Okay. So, early versions of Internet Explorer essentially supported ActiveX-based application where you could have the equivalent of Java applets, okay, but written in the Windows world. Okay, you needed essentially Internet Explorer to run these applications. Okay, so that's essentially a history. You will see that the original middleware essentially just supported basic RPC communication. Layered on top of that was OLE that allowed Office applications to communicate with one another. Layered on top was then ActiveX, which added web pages as one type of a document, and then essentially allowed you to write web-based application. Okay? And that essentially basically led to DCOM, and which is now turned into .NET. Okay? So essentially DCOM is a successor to COM, okay, and it essentially has the ability to do distributed computation. Okay? All of this was still single machine. Okay? You could take in OLE, you could essentially take Excel spreadsheet that you have on your disk, embed it into a PowerPoint. Okay, you are not doing this across machine. DCOM essentially allows you to do all this using distributed objects that goes across machines. Okay, so that looks like our more traditional distributed middleware, where clients and servers communicate and objects live across machines and so on. Okay. And here are some examples of how DCOM works and some relationship to similar concepts in Java. Okay. So there is something called a type library in DCOM, okay, which is very similar to Corebar's interface repository. That's essentially a database that keeps track of all the different types of objects that are stored in there. Okay. And then there is a service control manager that is similar to Corebar's implementation repository, which is not shown here, unfortunately. Oh no, actually it is shown here. That's called SCM, that talks with the registry. The registry is essentially the type library. So on disk, it keeps track of what objects have been registered and so on. And then you can use the service control library to query it and say what services are available. You will see there's a client application here. The server application is implemented as objects. And then what is underneath here looks very much like an RPC system. Okay, so you have marshalling and demarshalling of arguments, you have the stub, and you'll see there's a COM layer here, which looks very similar to the ORB layer in Corebar, okay, which is facilitating communication between the client and the server. Okay? So most of the, and then you have something called Microsoft RPC that's allowing you to communicate between the client and the server. Okay? So as you go through these different distributed middleware systems, okay, you will see that each was designed for a different purpose or a slightly different purpose or different platform, but underneath they use very similar concepts. They all use RPCs or RMIs. Okay, they will all have this notion of a distributed object. Okay, they'll all allow you to use various kinds of services that are built into that middleware, so you don't need to write code and whatnot. So there are, just as EJB supported different kinds of classes, okay, even in DCOM you will have various kinds of classes and persistent objects. Okay, so you will see essentially this notion of a term called a moniker that's used there, which is this notion of a persistent object in DCOM. It's a very similar object, very similar concept to persistent objects in Java. Okay, essentially the middleware will take care of storing the state on disk. If you restart the application, your object state does not go away. Okay, by definition, most of the objects you have in your code, if you shut down your process, that object is gone. Okay? If you have persistent object, you can shut down your application and restart it, you can get that object back exactly the way it was before you shut it down. That's the notion of a persistent object. Okay, so most of these more advanced middleware systems also support persistent objects in addition to our traditional transient objects. So the traditional objects are transient, which means they're essentially gone, they're volatile. They're gone if you shut down the code. But here objects are persistent, and in order to get back your object, you need a handle or a reference to that object. That in DCOM is called a moniker. It's essentially like a URL which allows you to say, I want this object, and that object is essentially stored on disk. Okay? And then you can recreate it using that handle and bring it back into your process after you restart it. Okay? So that's essentially the new feature that most of these distributed middlewares provide that we have not seen before. Okay? The ability to persist objects across application restarts and whatnot. Any questions here? Okay, and you will see that there are different ways to provide references. You can just provide a reference to a file, that's called a file moniker. You can essentially provide a reference to a URL, which basically allows you to get a URL as an object. This is the most common one, which is the class moniker that says, go persist this class object, and then you can recreate it at another time. You can have composite objects and so on, which I will not go into. But there are different kinds of these persistent objects that you can have in DCOM as well. Okay. Okay. So the last kind of middleware that I'll talk about is very different from all of these. Something you may not have ever encountered. Okay. Everything I talked about so far builds on an object-oriented world. If you know RMIs, it's easy to then say, okay, I know those concepts, I can use them in a distributed middleware framework. Okay, but there is this other kind of middleware that is meant for distributed coordination. Okay, so, and we will see how this is different from most of the others that we talked about. Okay, so to understand this middleware, I need to first provide you some background, and I'll talk about this notion of coordination models. Okay, so let's assume you want to write a distributed application that has some components. Okay, components want to interact with one another. If you look at the interactions, or the you can say whether the interactions, how the interactions occur in time and space. And so that's basically two dimensions. One is called temporal dimension. The other is referential dimension, or is called a spatial dimension. Okay? And depending on whether you are coupled in time or coupled in space, you will get different kind of interactions. And I'm going to start with real world examples first, and then we will see how that actually maps into a distributed coordination system. Okay? So if you talk to someone else as a person, if you talk to someone else one-on-one, okay, you're talking to that person at the same time, okay, and you're talking to that person also at the same location. Okay, so that's essentially called coupled in time and coupled in space. That's direct communication. Okay, you're just talking to someone, talking to your friend or some such thing. Okay. Now, if you are communicating with your friend through email, okay, essentially you are decoupled in time. You send a mail, but when the mail gets read might be at a later time. So the communication is not at the same time as if you are talking to someone face to face. Okay. So you are now decoupled in space. Okay. But you are still coupled in, rather decoupled in time, but you are still coupled in space in that you know who you are talking to. Okay. So you address that message directly to your friend. Okay. So you are still coupled in space. Okay. Now, let's say you want to call a meeting. Okay, so let's say you and your friends want to meet somewhere, so you call a meeting and say, let's meet at the student union at 5 o'clock. Okay? Such a group communication is going to be coupled in time because you're all going to gather there at 5 o'clock and talk. Okay? But it may not be coupled in space, not space, referentially coupled, because you may not know ahead of time who all are going to come. You just basically announced a meeting and say, let's all get together at 5. But you may not know exactly who is going to show up and who may not show up. So you are basically going to be decoupled in the referential dimension. Okay? And the most general form is you are essentially communicating, but the communication is decoupled both in the spatial dimension and the temporal dimension, which means that you might send a message. You don't know a priori who that message will reach, and you don't know a priori when that message will reach. Okay? So if you write an application where communication between parties occurs such that you don't know when messages might reach someone or whom the message might reach, you are going to get this very general model which is called generative communication. Okay? Now you might ask a question saying, why would I send a message if it's not meant for someone? What kinds of models are suitable in this kind of scenarios?
I'm thinking of stuff like Kafka, which is, yeah, you don't know exactly who's going to read whatever you're sending, but you know that someone probably wants it.
Yes, so I think Kafka is a good example. I'm going to talk about Genie as well, but before that, I will introduce some term, okay, which will make it clear why communication like this even is a good thing. Okay? So another way to think about this, decoupled in time and space, is a bulletin board based communication. Let's say if you go to the kitchen here, there's a bulletin board. You can post a note there saying, I am moving, I am going to sell my furniture. You put a note there. That message is not addressed to anyone specifically. You just put up a note. Okay? You don't know if someone will actually be interested in what you posted, okay, or when they might actually be interested. So you just have put up a note saying, I am interested in selling my furniture. If you are interested in buying anything, contact me, and you put your phone number there. Okay? So in a bulletin board architecture, you can essentially post a note which is not addressed to anyone. It's posted to the general public, but not addressed to any one person in particular. Unlike an email which you send to a particular person. Okay, so that you send an email to a friend. You just don't send an email without an address. Okay, you always address an email to a specific person. When you post a note on the bulletin board, it's not addressed to any one person in particular. Okay? So you are not sent it to any one party. Neither do you expect that anyone will actually look at it at any given time. Someone else might come at some later time, and what time you don't know. If they might look at the note, they may or may not be interested in something like this. Okay? So bulletin board architectures are examples of applications which are in the generative communicative space. So messaging is decoupled in time also. When you post a message, it's not meant for anyone in particular. When someone comes looking for a message, you don't know if there will be a match. So you might go to the bulletin board every day saying, is someone selling a car because I'm interested in one. Okay? You don't know if anyone has posted any such message, but if there is one, you will find it. Okay? So that's an example of a bulletin board architecture, and you can actually write distributed applications that use this example. Okay, Kafka is one, but I'll show you several other examples where this kind of scenario is used for communication. Okay? This is unlike anything, any client server application you have written, because most of those will actually be direct. Okay? Or if you're using message queuing systems, you will be here. Okay, so we have looked at this, we have looked at this. This one we have not looked at very much, but this definitely we have not looked at. So this is a very different kind of middleware. Is that clear what we are starting with? Okay. So now we'll look at, there are many systems that use generative communication. I'm going to talk about Genie, which is a Java-based generative communication system. Okay. So in this, so there are several interesting features when you write applications using Genie or many of these models. One is the ability to discover new services. Okay, so here is an example of where you might use something like this. So let's say you take your laptop or your phone or your tablet and you go to some, let's say a coffee shop or someone's office, your friend's office. Okay? You connect it to a Wi-Fi network there. Okay? Now say you want to print something in that environment. It's not your local network, it's someone else's Wi-Fi network. So if you want to print it, what would you do? You want to print a document in some foreign Wi-Fi network, how would you go about doing this? Okay, the standard way or the old way is you'll ask your friend, do you have a printer? Okay, what's the network address of that printer? You will configure a new printer on your machine. Okay, if necessary, you might have to install a driver or all of that. And then once you're configured, you will actually print to that printer. Okay, that's one way to do it. Okay, very cumbersome, highly manual approach to doing it. Okay, now what if every printer that's sitting on a network is advertising itself, saying I am a printer. Okay, and it posts this note on a bulletin board. Okay. So now if your machine goes into an environment, it can just discover all kinds of services that are near it. It can say, I can see 5 printers on this local area network. Okay. And if you say print, it will say there are 5 printers near you. These are the printers, because it's gone and discovered them by itself, because each printer is advertising itself on a bulletin board. Okay, so now if you want to print, you can just say, okay, there are 5 printers. Let me look for one that's very nearby, and then I just print and you are done. Okay, you don't need to go find the IP address of the printer. You don't need to ask anyone. Okay, the printers are advertising themselves on the bulletin board, or your machine has actually gone and found them, and then it's showing you a list. Okay, so that's an example of making configuration of services in any network much easier. You don't have to do it manually. Services are advertising themselves. This is equivalent of saying, going and posting a note saying, I am printer X and this is HP model, color or black and white or whatever, IP address. And then every machine can just go and discover all sorts of services that are near it. Okay? Now there are many operating systems that already do that today. On a Mac, this is called Bonjour printing, because it will basically go and it's also called zero-con for zero configuration, if you've heard of that term. Okay, you don't need to pre-configure anything. Services are automatically discovered and then you can configure them. Because there are equivalent things in the Windows world as well, where you can go and find these services. Okay, so this is essentially clients can discover services that they become available, and so there is essentially a bulletin board architecture that allows you to post these services and discover them and so on. Okay. Now you can actually build any other kind of application in the same way. Okay. I just gave an example of a machine trying to find a printer in a foreign network, but any application can be written this way. Okay. You write code of your components of your application, they go and advertise themselves using a bulletin board. Okay. And then other applications can find either services or data using the exact same model. You can post any data that becomes available on the bulletin board. Some other application component can come and query the bulletin board and find if there is matching data. Okay? It's somewhat like publish, subscribe as well, if this is just looking at data, but you can also discover services in this fashion. Yeah, so I'm going to show you a picture here, So this is an example of Yes, your question there.
So understanding, it's easy to understand how you can discover data, but how do you discover services?
How do you discover services? Services advertise themselves the same way. Okay, so just as in the bulletin board example, printing as a service, right? So you basically say, I am a print server, or I am print server on a printer, and you just advertise yourself. So you discover that service, and we'll assume that the print service uses some well-known protocol that you can use to communicate. Okay, otherwise you wouldn't know how to communicate with that service. Okay, so I mean that's the general idea. Now, clearly, any service that you are trying to use, you need to know how to communicate with that service. Okay, if you don't know the interface to that service, you will not be able to talk to that service. Okay, so the assumption is either you will know that interface a priori because it's a standard protocol of some sort, or there's a way to figure that out.
So this means that if you have in a system, if you have 10 pre-configured services, but the system currently only supports 3.
Yes.
So when the rest of the 7, one of them comes about, you will be able to discover only one of the 7, which are not. So if you have 10 and only 3 are in your system right now, and you need to discover a new one, does it mean that you can only discover one of those 7 and not an 11th one, which you don't know?
Right. So the question is, if there are some number of services and you discovered some subset of them, and you want to discover more, how do you go about doing that? And so there are 2 ways of doing this. Okay? In one case, you may go and discover every single service that's out there and then just find for matches. In the other case, you specifically query for the kinds of services you want and only discover them. Okay, so there are those 2 approaches. Now, in the system administration or zero configuration case, your machine goes and actually discovers every service that's out there. In fact, if you connect your machine to a LAN, okay, this doesn't work on Wi-Fi because this requires you to do broadcast and whatnot. But if you connect your machine to a LAN in this department, you will see that a Mac will go and find a whole bunch of printers. And if you go into the print panel and say nearby printers, it will show you a list. So it's gone and discovered every single one. Okay? Now you could have said, I only want to look for a color printer. Okay? And then you will have to go and query for attributes saying type printer and model color or some such thing, and then only discover that. So when we talk about Java, we can see this basically it depends on the kind of queries you do, and you can rediscover services. It's not like the set of services will be static. Services can come and go. New data can get posted to the bulletin board at any time. So you can rerun your query and rediscover services and so on as well.
But would this mean that you can only discover services which you expect to discover?
Okay, question is, could you only discover services that you expect to discover? That depends on how you pose the query to the bulletin board, right? So if you say, find me star, which means match everything, you will get everything. You may not know how to communicate with some of them, but you will find them. Discovering is different from communicating. Discovering just says, what is near me? I may find a printer, but I may still not have a driver to talk to the printer. That's different from saying, I found a Canon printer. I may not know how to print to it because I might need a Canon driver to print to it. Okay, so discover is independent from actually being able to communicate and do something meaningful with the service. Okay, you had a question there.
The bulletin board is like a Pyro name server or a Kafka broker, right? I mean, just to understand it.
The bulletin board is essentially can be implemented in many different ways. It basically uses what's called a bulletin board architecture. Of course, directory services also allow you to post services and discover from directory services. Okay, bulletin board is a slight generalization of that because you can actually post data, not just services. Okay, in Kafka, you can do the same thing, right? So I think directory services only allow you to discover services. You can't post data and query it from a directory service. Okay, in a bulletin board, it doesn't matter what you're posting. You're just posting notes. Okay, what is the note? Does it contain some data? Does it contain advertisement of a service? That's up to you because that allows you to do whatever you want with it. Okay? Yes.
Does UPnP have anything to do with this? And if so,
okay. So question is UPnP is acronym for Universal Plug and Play, which is supported to also discover services and advertise services. It does not necessarily use a bulletin board architecture, but it does borrow directly from the zero configuration concept that I mentioned, where you can essentially broadcast your presence and others can discover your presence. Okay, so ZeroConf, UPnP, Rendezvous, there are many of these protocols that have been designed that basically use similar concepts. Okay, those are all services in the system administration kind of zero configuration administration kind of domain. Kafka is more for data processing. Okay. Genie allows you to write any arbitrary Java application just to use Java spaces, okay, which is their bulletin board. Okay, so in Genie, essentially you have the notion of a Java space, that's the equivalent of our bulletin board. Any application can write to the bulletin board, which is the equivalent of putting up a note. So you'll see here there are notes of different kinds. Some notes could be replicated and we'll see why. Okay. And then you can actually read. Read could be in the form of a query saying, find me all notes or tuples that match attribute T. You could say, find me all printers. There may be many different kinds of nodes. You could say, find me all printers, and then you will only get all nodes that essentially have type printer. Okay? You can just get the notes or you can delete the note as well. It's the equivalent of taking a note off, saying, or you can just say, I look at it, but I leave it on for others to discover. Okay, so that's the basic concept of a Java space. So you can write to that. So essentially, this is implemented as a distributed database internally. Okay? You can write tuples to your database. You can query for tuples. You can remove tuples. But that's and then you can also implement this notion of a publish subscribe, where rather than querying repeatedly, you can say notify me whenever a new printer is found. Okay? Or notify me whenever a new note that matches this attributes is actually posted to the bulletin board. In this case, you basically have a callback. So that's your client. You have a callback, and whenever C is actually inserted which matches your attribute, you will be told that a new note has appeared that matches your criteria. Go and look for it on the bulletin board. Okay, so either you can do poll based or notification based delivery from your tuple space. Okay, so those are the two ways by which you can actually post notes and take notes. So the important thing here is communication is taking place without messages being addressed to anyone in particular. Okay? So if you want to send a message from one entity to another, you are not addressing it saying, take this note A and deliver it to this process. You just post it on the bulletin board and then assume that the other party is going to do a query for that note and take delivery of it. Okay? So you can still enable communication, but you are not having a direct communication, or neither is this coupled in time, because once you post something, you don't know when someone else will come and take delivery of it. Very similar to a bulletin board concept. Okay, here's an implementation of two different implementation of Java spaces. Okay, this is a physical implementation. You'll see that Java spaces are replicated across machines. The distributed database I talked about can actually get replicated on multiple machines, and there are two ways you can configure it. Okay? You can say writes are broadcasts, which means that whenever you write something, you will write it to each of the replicas. Okay? That is why you will see in this previous case there are actually 2 versions of A and 3 versions of B, because this dotted box is a logical representation of the Java space, and the physical one says I've actually replicated my database, and when I write something it gets replicated to all of it. If you replicate to all of your bulletin boards, then reads are local. Okay, this is similar to, let's say I put a bulletin board on floor 1, floor 2, floor 3. When I post a note, I go and post it in all 3 floors. So then somebody only has to look at their local bulletin board to find a match. Okay? So that's basically I replicate my writes, reads are local. You can also have the opposite, where writes are local. I can go and post a note on only one. Okay? Then if I want to find a matching note, I better broadcast my read, which means I query all the replicas, saying, because I may have to go on the first floor, second and third floor to find a match, because each note is only posted on one of the 3, not all of the 3. Okay? So you can essentially configure them as writes are broadcast and reads are local, or the opposite, which is shown on the next slide, where write is done locally, but reads will actually have to go to all the replicas and say, do you have a matching attribute, matching note for me? Okay, so you can configure it in the Genie case in either of those two ways. Okay, and that will allow you to construct this application. So this is just an example. We haven't actually looked at this kind of application, distributed application before, but it's something you should know. They're out there. Some of you are familiar with Kafka. Okay, there are modern systems like Kafka that use similar concepts, and Genie was one of the early ones that was designed in the Java world that allowed you to implement applications of this sort. Okay, so very different way of writing an application. Okay, uses concepts from publish subscribe, uses essentially uncoupled temporal and referential communication, where messages are sent but not to any one application process in particular. They're sent to a bulletin board, and others will take delivery of it from there. Okay, many applications are still written this way. Okay, although direct RPC style communication is by far the more common case. Okay. So we are going to stop here today, and then next time we will continue with a little bit more on distributed middleware. Specifically, I'm going to talk about data processing systems like Hadoop, Spark, MapReduce, and those kinds of applications. Okay. So let's stop here for today.